This is section 7.4 of accelerated geometry, corresponding parts of similar triangles. There are two investigations. They start on page 391. Each of the investigations leads you to a conjecture. So a good thing to do would be to do those investigations to arrive at the conjectures for today. If you go to My CMH and you go to links, chapter 7, you will see for section 7.4 that there is a video on corresponding parts of similar triangles, and that might also be a good thing to look at. I am going to also go to Sketchpad here, where there is an investigation set up for the first investigation. So what this says is, if two triangles are similar, what about their altitudes, medians, and angle bisectors? Okay, so if I take these two triangles and I take the smaller side and the larger side, and I find out what the ratio of those sides would be. So this would be smaller side divided by the larger side, and I get 0.7. Okay, now I'm going to take the altitude. I've measured the altitude of each of them, and I'm going to do the same thing. Go to my calculator, and I'm going to take the smaller one, the smaller triangle's altitude divided by the larger triangle's altitude. And when I do that, look at that. I get the same ratio. Okay, what about the angle bisectors? So here is my calculator. If I take the angle bisector in the smaller triangle and I divide it by the angle bisector in the larger triangle, I get the same ratio. And same thing with the medians. If I take the median in the smaller triangle and divide it by the median in the larger triangle, I get the same exact ratio. So if two triangles are similar, then their altitudes, medians, and angle bisectors are proportional to the corresponding sides. So the corresponding sides are in the ratio of 0.7. That means the altitudes are in that same ratio, the angle bisectors are in the same ratio, and the medians are in that same ratio. And this would be conjecture number 62 on your conjecture list. Now we have one more conjecture. Okay, look what happens here. I have a triangle, and I create in here an angle bisector. So I've constructed that as an angle bisector. Okay, now look what happens. If I take the sides, if I take this side divided by this side, I get 1.84. The angle bisector cuts the opposite side into the same ratio. See this? DE over BD is the same exact ratio. So if you have a triangle and you have one of its angles split in half by an angle bisector, the ratio of the two sides that are on across, or what I say, connected to that angle bisector, so the ratio of this side to this side is the same ratio as the ratio of the two parts that the angle bisector cuts into on the other side. This piece here over that piece here. Now I could also have gone this way. This over this. Do it again. This over this. The top side over the bottom side is the same ratio as this top side over this bottom side. So this is conjecture number 63 on your conjecture list. A bisector of an angle in a triangle divides the opposite side into two parts whose lengths are in the same ratio as the adjoining sides of the triangle. Now, if I go back, here is the list of the conjectures. So 62, if two triangles are similar, then the corresponding altitudes, medians, and angle bisectors are proportional to the corresponding sides. And conjecture 63, a bisector of an angle in a triangle divides the opposite side into two segments whose lengths are in the same ratio as the lengths of the two sides forming the angle. Now that conjecture number 63 is going to be helpful to us when we do a construction. So I'm going to bring up some paper here to write on. I lost it. See if it will come back again. Okay, now I have two of them. Okay, so now here is the problem. I have this segment, and we're going to call it AB. It says, break segment AB into the ratio of 2 to 3. So that means I want this AB, so here's my sketch, to be 2 parts here and 3 parts here. Okay, now what do I know? I know that conjecture that says the bisector of an angle in a triangle divides the opposite side into 2 segments whose lengths are in the same ratio as the lengths of the 2 sides forming the angle. So this is what I'm going to do. I'm going to take a ruler, which I'm really not because I can't on my screen, and I'm going to open up my compass to any length that I want, and the highest number I need is 3. So I'm going to chop off 1, 2, 3 units. Okay, now I'm going to open up my compass from here to here, so that would be 2 units long. I'm going to stab in at A, and with that compass opening of 2 units, I'm going to create an arc from A. Okay, then I need a side that is 3 units. So I'm going to open up my compass from here to here. That's 3 units long. I'm going to stab in at B, and with that opening of 3 units long, I'm going to make an arc. The point where they intersect, if I connect it to A, that's the side of a triangle that is 2 units long. And if I connect it to B, that would be a side of a triangle that is 3 units long. Now, back to the conjecture. A bisector of this angle in the triangle will divide the opposite side into 2 segments whose lengths are in the same ratio as the 2 sides forming the angle. So if I now stab in here, go across, and do an angle bisector, so stab in here and make an arc, and with the same opening, stab in here and make an arc, this would be my angle bisector. The angle bisector splits the opposite side into the same ratio as the ratio of the sides forming the angle. So that would split that into a ratio of 2 to 3. Now, it does not mean that they are actually 2 units long, because here I made this be 2 units long, and you can obviously see that this is longer than this. But the ratio is going to be the same. So this is like 2 times something, and this is 3 times something. But if I take these two numbers, what they actually are, and I do a ratio of them, they're going to have a ratio of 2/3 or 0.6 repeating. Okay, that is the lesson for today.